Have you ever just stopped and thought about the invisible world that's, well, literally powering our lives? Every single device you use, from your phone to your car, it all runs on electricity. And that's a force we can't see or hear or touch, but somehow we've learned to command it. This is the story of how we managed to do that. How we learned to see and even speak to that invisible world.
You know, to work with electricity, we basically had to invent brand new senses for ourselves. We built all these amazing instruments, from pretty simple multimeters to really complex oscilloscopes. Each one is like a special window into that unseen realm, letting us measure and understand and, yeah, ultimately control it. But that brings up a really fascinating question, right? If electricity is just this silent flow of electrons, how in the world do you even begin to measure it? How do you give it a number or a shape or a direction? Well, that's the big mystery we're going to unravel in this explainer.
Okay, so our journey doesn't start with some clever gadget. Nope, it starts with an idea. See, before you can measure anything at all, everybody has to agree on what the measurements actually mean. You've got to create a language first. I mean, think about it. A measurement is totally useless if my volt is different from your volt. So the very first step was creating these standard units, a shared universal vocabulary for things like length, mass, time, and of course, electricity. This is the absolute foundation for everything that comes next.
Now, here are two words we mix up all the time, but they are so crucial here: accuracy and precision. Accuracy is all about hitting the bullseye, how close your measurement is to the real, actual value. Precision, on the other hand, is about consistency. It's about how close your repeated shots are to each other, even if they're all hitting the wrong part of the target. For a measurement to be any good, you've really got to have both.
And you see these standards at work every day. Just take temperature. Because we all agreed on units, Celsius, Fahrenheit, Kelvin, and we have standard formulas to switch between them. A temperature reading in New Delhi makes perfect sense to an engineer in New York. It creates this global system where we all understand each other.
Okay, so we've got our language down, but how do we get the invisible world of electricity to actually speak it? Well, the first huge breakthrough is figuring out how to make an electric current cause physical movement.
And the hero of this chapter is the galvanometer. It's a simple, really elegant device with just one job: to detect the presence of even a tiny little electric current. It wasn't about measuring how much current just yet. It was just about proving it was there at all. This was the very first knock on the door of the invisible world.
So, how does it work? It is absolutely brilliant. It's all based on something called the motor principle. You pass a current through a coil of wire, right? That creates a tiny invisible magnetic field. That new field then pushes against the field of a nearby magnet. And that physical force is what actually moves a needle. Just like that, an invisible current makes a needle twitch. An absolute game changer.
And you can really see how this tech grew up. Early instruments like this beautiful old Wheatstone bridge were these complex mechanical wonders designed for very specific jobs. Now compare that to the digital multimeter on the right. That little thing you can hold in your hand does the job of a whole workbench of that older equipment. But it's all built on that exact same fundamental idea, turning electricity into a number we can actually read. So, detecting a steady current was one thing. But what about signals that are constantly changing, zipping back and forth thousands or even millions of times a second? A simple needle just can't keep up. We needed a way to not just detect electricity, but to literally draw a picture of it.
This was the next huge challenge. Think about it. If a radio wave or an audio signal is vibrating incredibly fast, how could you ever see its true shape, its waveform? A simple mechanical pointer would just be a blur. We needed a faster pencil, a much faster pencil. And the answer was the cathode ray oscilloscope, or CRO. Instead of using a physical needle, the oscilloscope uses a weightless, lightning-fast beam of electrons as its pen. This beam can be moved almost instantly, which lets it trace out a perfect picture of even the most ridiculously fast electrical signals.
So how does it pull off this magic trick? It is so ingenious. Okay, you've got an electron gun that shoots a focused beam of electrons. The electrical signal you want to see, that's your input voltage, is used to steer that beam up and down. At the exact same time, another circuit sweeps the beam steadily from left to right. And when this speeding beam hits the special phosphor coating on the screen, it makes the screen glow, literally drawing the signal's shape for you in real time.
Yeah, the secret sauce to the whole thing is a property called fluorescence. That phosphor on the screen, it just soaks up the energy from the electron beam and then spits it back out as visible light.
It's this amazing physical phenomenon that finally let us turn a super-fast electrical signal into a stable picture we can actually look at.
And this is where you can really see the power of the oscilloscope. When you feed two different signals into the horizontal and vertical inputs, you get these intricate, just beautiful patterns called Lissajous figures. And they're not just pretty pictures. Each one is a precise visual map of the relationship between two signals. It's like finding hidden art inside of electronics.
All right, let's jump forward to the modern era. The fundamental principles, believe it or not, haven't really changed. But the tools we use, oh yeah, they've gone through a total revolution, moving from dedicated physical boxes into the super flexible world of software. You see, the spirit of the galvanometer and the oscilloscope is still alive and well. But today, instead of being stuck inside separate, bulky instruments, their functions are all integrated into compact, powerful devices driven by really sophisticated software. We basically took the hardware and taught it how to speak the language of computers. And this leads to the idea of the virtual instrument. The whole point is to stop thinking of an instrument as a box that does one thing. Instead, you use a standard computer with some plug-in hardware. The software on the computer is what defines what that instrument does. Need an oscilloscope? You load up the oscilloscope program. Need a spectrum analyzer? Just load that program instead. The hardware is the same, but its function is virtual. It's all defined by code.
And this is what that looks like in practice. This is a front panel from a program called LabVIEW. All those knobs and dials and graphs, none of that is physical hardware. It exists only on the screen. It's a completely user-defined instrument that lives inside the computer, ready to be reconfigured for a million different tasks.
So why is this such a big deal? Well, the advantages are huge. These systems are incredibly flexible. They use the ever-increasing power of our normal PCs to do all the heavy lifting for analysis and display. You can connect them over networks, and they slash costs because one piece of hardware can suddenly become a dozen different instruments. It's just a smarter, way more efficient way to measure the world. Which kind of leaves us with one last really cool thought. Our whole quest started with just trying to see a simple electric current. Now our tools aren't even physical objects anymore, they're powerful pieces of software. So as this virtual revolution keeps going, what other invisible forces, what new hidden worlds are we about to make visible next?